Hi, everybody. In this chapter, we're going to be discussing electrochemistry. Simply defined, electrochemistry regards the interchange between chemical and electrical energy, basically how we can transform materials into electricity and vice versa. It is so important for a large variety of things in both industry and elsewhere. And we are going to talk about it in many different contexts, but I just want to introduce the topic by giving you some idea of just how important electrochemistry is and really how it affects your everyday lives. Um, Electrochemistry is essential for synthesis, making stuff that we like to use. I believe in the past we've talked a lot about aluminum metal and how important aluminum metal is. Aluminum metal cannot be synthesized without electrochemical processes. Um, Similarly, silicon metal, silicon really is a metalloid, but it's essential for use in microchips, so in all of your electronic devices. This cannot be prepared without electrolytic processes. Hydrogen gas. This is essential for fuel cells, so people fantasize about fuel cell vehicles. Hydrogen cannot be synthesized in its elemental form unless you have electrochemical processes. Chlorine. So oxidized chlorine is used in bleach and disinfectant. It's used, unfortunately, as a chemical weapon as well. It is synthesized from salt, basically through electrolytic processes. Sodium hydroxide, a ubiquitous ingredient to prepare so many things, also prepared by electrolytic processes. So without electrochemistry and electrolysis, all of the things we use on a daily basis wouldn't really exist in their current form. So electrochemistry is hugely important to make materials. One thing that's important to think about with electrochemistry is it's really just an applied version of thermodynamics. So in the last chapter, we learned about free energy, which we denoted with a delta G. And we learned that whenever processes have a negative delta G, they're said to be forward spontaneous. In this chapter, we basically have a version, kind of free energy, but instead of free energy, we call it voltage or electrochemical potential, and we denote it with capital Greek letter epsilon. So voltage, also known as electrochemical potential, is really the same thing as free energy, but just with the sign reversed. So they're related to each other through a constant. We'll talk about that equation a little bit later on. So that's the proportionality fiche. Electrochemical potential is proportional to the negative of the free energy. So you can use electrochemical potential to gauge the spontaneity of a process. And basically how much energy it's going to require or give off. Another very important application of electrochemistry is batteries. Batteries are just simply electrochemical cells that store electricity and kind of allow us to harness that electricity to use whenever we want to. Okay, so this is, of course, hugely important in the modern world where a lot of our devices rely on these electrochemical cells that make electricity portable and easy to use, and they're often rechargeable. So to recharge a dead battery, you kind of have to push the reaction back up the hill from a thermodynamic standpoint. Hugely important as well is the electrochemical process of corrosion and trying to prevent it. So billions of dollars go into this. For example, rust is very problematic for the function of a lot of different materials, items. So trying to prevent corrosion is an enormous part of a lot of industrial processes. And finally, electrochemistry is huge, as you guys know, in biology. Okay, so there are so many biological processes that are really just electrochemical processes. And of course, the classic one is aerobic respiration and the electron transport chain that basically reduces oxygen. So we use oxygen as an oxidant to break down food. This is a hugely important electrochemical process, and its opposite from a thermodynamic standpoint, of course, is photosynthesis. So photosynthesis produces oxygen as a byproduct of the fixation of carbon dioxide from the atmosphere into biomass. So these are two kind of sort of equal and opposite biological processes that are electrochemical reactions. There are many, many other examples as well. Nitrogen fixation comes to mind as a very important example. So nitrogen in the form of N2 gas is ubiquitous in the atmosphere. And organisms like bacteria are able to take that nitrogen and fix it, so incorporate it into biological molecules. And that's a very complicated electrochemical process that is mediated by a lot of different enzymes, such as nitrogenase, for example. Okay, so a lot of biology hinges on electrochemical processes. So in this chapter, we're going to be talking about electrochemistry kind of broadly defined. And there are a lot of topics from last semester that you should review, because last semester you were introduced to redox. So you should review the idea of oxidation states. So you might remember that elements in their pure form, in their elemental form, have a zero oxidation state. For example, if we have like solid iron, it has an oxidation state of 0. Some elements are diatomic in their pure state, like oxygen gas. It would have an oxidation state of 0. Bromine exists as a diatomic liquid. It would have an oxidation state of 0. So elements in the pure state have 0 oxidation states. And the rest of the oxidation states of elements in chemical compounds, you can kind of figure out from the context. So, for example, let's take a compound like sodium chloride, very simple. We know that sodium is an alkali metal, and it has a +1 oxidation state. Chlorine, in this particular instance, is a halide with a -1 oxidation state. And you can kind of use the clues about the different components in a chemical compound to figure out what their oxidation states are kind of algebraically, right? So we know that calcium is an alkaline earth metal cation, so it would be 2+, and oxygen must be 2- to balance that out and give us a neutral compound. Okay, so that's very basic, but all of that stuff is stuff that you guys should really review before getting into this chapter. So what the first topic that I really want to talk about in this chapter is the balancing of redox reactions. So for this, you really need to be able to assign oxidation states. I have provided this to you as a handout that's uploaded to Blackboard as a PDF. So you have what I'm showing you on the screen right now as a handout. These are instructions that I have written to allow you guys to balance redox reactions in acidic solution. You are going to be responsible for balancing redox reactions in acid only, not in base. So your book has two different explanations, how to balance redox reactions in acid and how to balance redox reactions in base. You are only responsible for doing it in acid. And I strongly recommend, and I'm going to really require, that you use this method called the half reaction method to balance redox reactions in acidic solution. Last semester, when you first learned how to balance reactions in general, you would balance them essentially by inspection, and you would balance them by basically guessing and checking the stoichiometric coefficients. And the goal of any kind of balance is to achieve balance in both charge and mass. So you're looking for elemental balance, and you're also looking for charge balance. So the charges have to be balanced on the reactant side and the product side. The ones last semester that you balanced by inspection were a little less complicated than the ones this semester. So the half reaction method here is going to provide you a very systematic way of balancing redox reactions. And I am going to teach you guys how to do it using this handout. and using a couple of example problems, okay? So I will do that in the next lecture. So there is my introduction to chapter 17, and in the next lecture, we will practice balancing redox reactions in acidic solution, and I'll go through the strategy here. So you might want to familiarize yourself with this handout before the next lecture. Thank you.